Okay, buffers contain both the acid and the anion. They're both present, and so we have an equilibrium between them. And I can add large amounts of acid or base without affecting the pH much. So even if I add a large amount of acid or a large amount of base to a buffer, I'm not going to get a large pH change. I will get some pH change, but it won't be large, equivalent to what I would get if I added the same amount of acid or the same amount of base to water. Okay, it turns out that a buffer works best when I have the concentration of my acid equal to the concentration of my anion, if I have an acidic buffer. If I add a base, the acid can absorb it by giving up hydrogen ions to neutralize the base and increasing my concentration of A-. If I add an acid, the A- absorbs the hydrogen ions and increases the concentration of HA, and so that decreases my overall hydrogen ion concentration and minimizes the pH change. Now, the equation we've seen before when we've looked at equilibrium expression is Ka. If we rearrange it so that we write the expression in terms of the hydrogen ion concentration, we have the hydrogen ion is equal to Ka times the acid concentration divided by the anion concentration. Now, if I choose to take the log of both sides, either natural log or base 10 log, I'm going to get an equation that looks like something to the right, where I have the pH, so this is the log of the hydrogen ion concentration. I have the pKa, that's the log of the Ka, and then I'm going to take the log of this ratio. And the reason that this is flipped on this side compared with this is if I were to do it the way it's written in the left, then what I would have would be a negative sign. So if I want to go from the hydrogen ion and take the log of that, I would have the pH equal the log of the Ka, so that's going to be the pKa, and then it would be minus the log of the acid concentration over A-. Positives are preferred, so we go with the equation on the right. It's called the Henderson-Hasselbalch equation. That equation is actually given to you on your green sheet, and what it does is it helps us to relate the pH of a solution to the pK, or the acid dissociation constant, the log of that value. So let's take a look at using this. If I want to calculate the pH of a solution, 0.75 molar lactic acid, and we've got a Ka of 1.4 times 10 to the negative 4, and in that solution, to make it a buffer, we have 0.25 molar sodium lactate. So the first thing they're asking us to do is write an equilibrium between the acid and its corresponding ion. So we're just going to use HA for lactic acid, and it dissociates into hydrogen ions and lactate ions. So there's our expression. Now I need to write the K expression. So it's Ka, so Ka is going to equal hydrogen ion concentration times anion concentration over the acid concentration. And we're given Ka is 1.4 times 10 to the negative 4. So my initial concentrations here of lactic acid are 0.75 molar. And for lactate ion, it's 0.25 molar. And I need to find the pH. So I need to find the hydrogen ion concentration. So initially we'll say that's 0. So my equilibrium is going to shift to the right. So in my equilibrium expression, I'm going to have 1.4 times 10 to the negative 4 equals x times 0.25 plus x all over 0.75 minus x. Solving for x gives me my hydrogen ion concentration. Since my exponent is negative 4, the minus x in the denominator, the plus x in the numerator, can be eliminated. And so I have x, which is my hydrogen ion concentration, equal to 4.2 times 10 to the negative 4. So that allows me to have a pH, or that creates a pH for me, of 3.38. Okay, the other way I can do it with my new equation, if I wanted to, would be to say the pH, which is what I want, equals the pKa plus the log of the anion concentration over the acid concentration. So P8 equals a pKa, so I want to take the log of 1.4 times 10 to the negative 4, and I get 3.85, plus the log of my anion concentration, which is 0.25, over my acid concentration, which is 0.75, and I solve that, and I should get the same thing. I should get a pH again of 3.38. So either way can be used to solve these problems. Whichever way makes more sense to you is great. If we take a look at a basic buffer, we can do pretty much the same thing, only this time we're going to be using a Kb. So we have 0.25 molar ammonia and 0.4 molar ammonium chloride, and we're supposed to find the pH. So we're going to start out the same way. If we write out the equilibrium expression, we have ammonia reacting with water, get ammonium ions and hydroxide ions. So our initial concentration of ammonia is 0.25, ammonium ions is 0.4, and this is 0. So for our equilibrium, we've got 1.8 times 10 to the negative 5. Concentration of hydroxide is X. Concentration of ammonium ions is 0.4 plus X. Concentration of ammonia is 0.25 minus X. Again, since our exponent is the negative 5, we can cancel out the plus X and the minus X. And so we're left with our X equaling our hydroxide ion concentration. And we find that equals 1.1 times 10 to the negative 5 molar. Since this is so much smaller than our initial concentration, we know that our approximation is fine. If that's my hydroxide ion concentration, then my pOH is 4.95, which means my pH is 9.05. So that would be an example of a basic buffer and how to find the pH of a basic buffer. Buffering capacity. If we continue talking about buffers, buffering capacity pretty much is what you might think. It is the amount of hydrogen ion or the amount of hydroxide ion that the buffer can absorb without significantly changing the pH. Buffering capacity is determined by the concentration of the acid and by the anions. It really doesn't have much to do with the pH or the Ka. So if I have 3 molar solutions of my acid and my anion, how does their buffering capacity compare to solutions where I have 0.30 molar solutions of my acid and my anions, which is going to have a larger buffering capacity? The larger the concentration, the larger the buffering capacity. Again, when the pH equals the pKa, that's when I have the hydrogen ion concentration equaling the acid concentration, and then generally I also have the anion equaling that as well, and that is going to be my best buffer. Can absorb the most hydrogen ion or the most hydroxide ion under those conditions. All right, let's take a look at this problem. We're trying to figure out what is the change in pH when I add 0.01 moles of gaseous hydrogen chloride to 1 liter solutions. And I have a solution of acetic acid and sodium acetate, a solution A, and I have a solution of the same thing, but 0.05 molar for solution B, solution A, they're both 5 molar. And so I'm supposed to find the pH of the solutions. So for both of them, if we want to use our Henderson-Hasselbalch equation, we have pH equals pKa plus the log of the anion over the acid. But the anion and the acid concentrations are the same. This is a 1, so log of 1 is 0. So the pH here equals the pKa, and for this particular example, we have a pH of 4.74. All right, so that's my initial pH of both solutions before I add anything to it. Now, since I'm adding gaseous hydrogen chloride, effectively we're saying that the volume of the solution does not change. So I have 0.01 moles in 1 liter. So let's take a look at how that works for solution A. So I have the acid dissociating into hydrogen ions and anions. Our initial concentration is 5 molar, acid 0, and 5 molar for anions. Now I'm going to add 0.01 moles, so 0.01 molar hydrogen ions. So if I add 0.01, what that's going to do is that's going to combine with my anion. So I'm going to have 5 minus 0.01 for my anion. That's going to change my hydrogen ion a bit because I'll still get some hydrogen ions from HA dissociating. My HA is going to gain 0.01 plus. So now, if I find my new pH, it's going to look like this. So pH is going to equal 4.74, my pKa, plus the log of my anion concentration, which is 4.99, over my acid concentration, which is 5.01. And so when I do all the math for that, this is going to be 0.0017. So 4.74 minus that, my pH really doesn't change. pH stays at 4.74. So my concentration of acid and anion is 5 molar. It's way higher than the amount of hydrogen ion I'm adding. And so therefore my pH really doesn't change. I have a very high capacity buffer in this case. If I take a look at what's going to happen when I use solution B, again, I have the acid dissociating to form hydrogen ions and the anions again. This time I have 0.05 molar of my acid, and I have 0.05 molar of my anion. I'm going to add the same amount. It's going to do the same thing. So if I put 0.01 molar for hydrogen ion, it's going to react with the anion. So this is going to be 0.05 minus 0.01. And my acid is going to increase because the hydrogen ion combines with the anion. So I have 0.05 plus 0.01. So now, same equation, pH equals the pKa, which is 4.74, plus the log of my anion concentration. So I have 0.04 over 0.06. So I have a little bit different setup this time. So this becomes negative 0.18. And so my pH now is 4.74 minus 0.18. And so I have a pH of 4.56. So my pH has been lowered a bit by adding that gaseous hydrogen chloride, but the pH hasn't changed very much. So again, buffers maintain a very small pH change. This buffer changes more because it has a smaller buffering capacity, because the concentration is smaller.